Okay, we'll get started. Okay, before we start, is there any questions about the assignment or about last class? Okay. All right, so we're finally ready to start talking about PLONK, which is the actual zero knowledge protocol that hopefully you're learning more about now as a result of the assignment itself. So I'm going to go back to the very, very first thing I showed you in the first lecture. We'll go over that again, and then we'll start looking into the details of PLONK itself. Okay. So what are we trying to do? Up to now we have a whole bunch of, like, you think of it as a toolkit or a bunch of tools, building blocks for making a protocol. We're ready to make the protocol now, and we started with this problem where you have a function. There's some set of inputs. It might be a lot of inputs. And there's an output. And what you're going to do is you're going to prove that the output is correct given the set of inputs. Okay? And there were kind of like two worlds that you could live in. There's the world where the inputs are public, so everyone knows all of the inputs. And there's a world where some of the inputs are private, so not everyone knows all of the inputs. And so the statement that you're proving differs slightly between those two worlds. In the world where all the inputs are public, you're just saying this is the output of this function. You could recompute it yourself, but I'm going to give you a proof, and it's going to be cheaper and quicker for you to verify the proof that it's correct rather than just doing it yourself. The other variant where we have some secret inputs, which I've denoted W as witness, in this case, I'm proving to you that I know a set of values, and if you put these set of values into this function, it will produce this output. Okay, so that's the sort of statement that I'm proving. Okay, so these are your inputs. We'll call them public inputs. You may have some set of private inputs. This is optional. You have a function. The way we implement the function, or we describe how the function operates, is we describe it as an arithmetic circuit. Which means it has a gate. It's like a circuit with gates, but there's only two kinds of gates. There's an addition gate, and there's a multiply gate. And both of these gates, they just take two inputs, two numbers. The add gate adds them together, and so the output of the gate is the sum of the two. And then for a multiplication gate, it's the product of the two. Everything is done mod p, so that's the only other sort of consideration, where p is going to be a large prime number. And let me actually modify this slightly. I'm going to say mod q because we've used both p and q to describe large prime numbers, and kind of where you stick this cryptographically will match what we've been calling q as opposed to p, but that's a detail that you can worry about later. Okay, and then z is the output of the function. Okay. Mathematically speaking, all of the inputs are from ZQ. Okay, so they're just an integer between 0 and q minus 1. Okay, they'll never get bigger than q, even though you're adding them together and multiplying them, because as soon as they get bigger than q, then you're going to mod it by q, and so it's going to put it back in range. Okay, so these numbers will always stay in the range, and z will also be from zq as well. Okay, so we have a set, and these are integers. There's no decimals. They're just integers, and they never get bigger than q, and you keep modding them down by q. Okay, now this is what we call a universal circuit. Which means any circuit that you want to run can be modeled with this. Okay, it might be a bigger circuit because you only have add and subtract, or sorry, add and multiply gates. So it might be difficult to implement the circuit that you want with it, but it can be done in theory. Okay? No one's going to do this by hand anymore. Okay, if this was the 1980s, you would take an electrical engineering course and you would do this stuff by hand. Now we use computers. So you just write code, for example, for your function, you press a button and it spits out the circuit for you. So there's tools that do this, and there's tools that are tailored for the zero knowledge case as well, like CIRCOM, for example, is one tool that will do that for you. Okay. So everything we're going to do in class will be a toy example. Like I'll just show you a really small circuit. We'll figure out how you can do it with that small circuit, and then you can blow it up to be a big circuit if you want to. Okay. The circuits, you can think of them, they're kind of like computer programs. They don't have randomness, unless if you want to put the randomness in as an input. And it's like a one-shot computation. Like the inputs go in, you get your output, you're done. It's not like a program that sort of runs in the background and it wakes up every now and then, does something, goes to sleep and wakes up. It's not that kind of thing, okay? So in other words, you can basically do any computation. We tend to refer to it as a function as opposed to a computation just because of that reason. But anyways, F is very general. Like almost anything that you could imagine, you could use as your F, and then you could do a zero knowledge proof for it itself. Okay. So the output of the ZK system will give you a proof, which will always denote pi. And so it either proves that Z is correct. So this we call the SNARK system. Or it proves that it proves the prover, the person giving you the proof, knows a set of WI values or witnesses or secret values. They know a set of secret values such that the output is set. And this is the ZK SNARK version of it. Okay, so in the first world, all the inputs are known. There's just public inputs. So the only thing really to prove is that that is correct. And then the second world, there's some inputs. The person receiving the proof, we'll call the verifier. They don't know what those inputs are. The prover's not telling them, and so they're kept secret. So what the prover's technically proving is just that they know a set of values that will satisfy this function and will output it. Okay. All right, questions about this setup? Okay, so for simplicity, I'm going to make some simplifying assumptions. I'm going to try and I'll write them sort of in green. So the first one I'm going to make is just that we're going to consider this world. And at the very end, I'll tell you how to adapt it for ZK SNARKs. But for now, we're just going to consider the world. So we're just going to focus on SNARKs, meaning all input values are public. Okay. Then later we can revisit this, and it turns out to be like a fairly simple switch to make it so that you can have secret inputs, but we won't get bogged down on those details now. Okay, so let's pick an example circuit, and we'll try and do a SNARK for it. So this is what your circuit might look like. Let's say we have an add gate multiply gate. Maybe 2 more add gates. And a multiply gate here. Okay, I'm going to define 3 inputs. I'm going to give them actual concrete numbers. Okay, and so we'll say that 3 and 5 go into this input gate. We'll put 6, 7 into this output. I'm going to grab 5. Draw this a little better. And I'll put it as the input here. Then I'll take the output here and put it here. And I'll take the input here and put it here, and I'll take the output here and put it here. Okay. So there's a little circuit. Okay, so this is a pretty regular circuit. So there's a few things that aren't allowed. We're not allowed to do loops, so we're not allowed to take an output and feed it back into an input. So this is a circuit. I'll put no loops. And again, if this is a universal circuit, so the fact that there's no loops doesn't matter. Okay, it just, the only thing it matters for is you might get, if you're allowed to loop, you might be able to implement your circuit with fewer gates than if you're not allowed to loop. But everything that you can express as a circuit with loops can be expressed as a circuit without loops. It just might be a bigger circuit. Okay, so another thing you'll see is that we're allowed to take the same input and feed it more than one place. Okay. And similarly, if we have an output, we're allowed to carry it into different spots as well. So this output can be this input and this input. So it doesn't have to be like a clean, just one input feeds into one gate and every output feeds into one gate kind of thing. Okay, questions about this so far? Okay, so the next thing that we do is so I'm going to come to you, basically. I'm the prover. So in zero knowledge, you have a protocol between a prover and a verifier. This protocol can be one of 2 ways. It can be a back and forth protocol where the prover sends some stuff, the verifier sends stuff back, and then the prover sends stuff, and at the end they're satisfied. Or it can be what we call non-interactive. And in SNARKs, the N in SNARK stands for non-interactive. In that case, the prover just sends the proof to the verifier doesn't do anything. Okay? So the prover doesn't have to meet the verifier, they don't have to have a conversation. They can put the proof up on a website, anyone can come along and download it and check that the proof is. Okay? So for SNARKs, yeah.
Are we going to cover any interactive protocols?
Are we going to? Yeah, so what we're going to do is we're going to actually start with it as an interactive protocol. So I'm going to show it to you interactive, and then we're going to do a trick to make the interactive protocol non-interactive. Okay? So eventually we'll get to this being a non-interactive, which is what we want. But temporarily, I'll show it to you as interactive first, and then there's a common trick called the fiat Shamir heuristic. If you know crypto, that will make it will convert the non-interactive protocol into an interactive protocol. Okay. Now, even in the interactive form, the verifier is not going to do much. All the verifier is going to do is choose random numbers, and they're going to send it to the prover, and it's kind of like a challenge, and then the prover is going to prove that everything is correct as far as that random challenge is concerned. And if it's correct as far as the random challenge is concerned, you can infer that it must be correct for all the other values. That's sort of the flavor of it. Okay. This has a name, by the way. It's called the polynomial interactive oracle proof, or sometimes PIOP. Okay, but don't worry about that. That's just, you might see this, or on the podcast, you might hear people talk about the PIOP model or the poly-IOP model. That's what they mean. Yeah.
So I didn't understand that. What is prover to non-interactive and interactive?
Okay, so prover, so the zero knowledge is a protocol between a prover and a verifier. Yeah. And it can either be non-interactive or interactive. And so we're going to start with an interactive protocol and then we'll make it non-interactive. Okay. Okay, so what's the output of this circuit? Okay, so that's what I want to prove. The prover wants to prove what the output is. The prover is going to have to figure out what the output is. Okay, you can't prove what the output is unless if you do it yourself. Okay, so the prover is going to do it. And they're going to write down every intermediary value as they do it as well. So let's do it ourselves. We'll walk through. Now, I haven't told you what modulus we're using. I'm going to, before we were using mod 23 as an example. I have it in my notes. I'm going to use mod 96. So it's still a small example, but it's a little bit bigger. So from now on, we'll assume that Q equals 96. Okay, what's 3 plus 5?
8.
All right, so we'll write an 8 on this wire. So this wire here has an 8 on it, all right? What's 6 times 7? 42. It will get a little harder. What's 42 plus 5? So the 5, this just denotes that sort of hopping over the wire. So here I have a 42, here I have a 5, just that got carried over. So 42 plus 5, 47. Okay. We have an 8 plus a 42 here, 50. Okay. I told you it would get a little harder, so what's 50 times 47? Mod 96. All right, so it's, I would have to use a calculator myself, so don't feel bad. 2350 is it, but again, we're modding by 96. And so the answer will be 22 when you do that. Okay, why did we wait to mod this last number? Why didn't we mod any of these earlier numbers? They're all smaller than 96, so if they're smaller than 96, modding by 96 isn't going to do anything to it. Okay. So, but once they get bigger, then you can mod them down. Okay, so what this means is that for this circuit, if you have inputs 3, 5, 6, 7, the output is 22. Okay, all right. Now, what I want to do is I want to prove that to you without you executing the circuit. So I don't want the verifier to have to look at all of these values, okay? And the way we're going to do it is absolutely crazy for a circuit of this size, because we're going to use crypto, we're going to have, I can't do anything with that, sorry. If it bothers you, you can switch to the other side.
Shut it down.
Like shut the, it's probably the bulb. That's usually what the issue is. So yeah, if you don't want to have a seizure, you can go over. I can't turn it off too either. Sorry, but I don't think, I can't selectively turn it off. Unless if someone wants to reach up and press the power button on the thing. But the back one's flickering too. So you guys don't have to worry about that, but I have to sit there and look at it. Okay, welcome everyone to the other side. The grass is greener over on this side. Okay, so the proof I will do is absolutely bonkers for something of this size, but imagine a circuit where you have 100,000 inputs and you have like 500,000 gates or 1 million gates. Then what we're doing is actually quite reasonable, okay? Like all the crypto that we're going to throw at doing this proof makes sense in order for proving something of that kind of size. Okay, so the first step, what I'm going to do is I'm going to turn, I'll write in a darker color. I'm going to turn the circuit into an array or vector, depending on your notation preference. And I should note, I'm just going to note that the prover's doing this. So the verifier hasn't come along yet. So this is all things that the prover's doing to prepare themselves to give a proof to the verifier itself. Okay. SNARKs are not distinct for the prover. Okay, so the verifier is going to get something that's short and it's they don't have to look at the whole circuit, they just have to look at the one proof. But for the prover, they're going to have to look at the circuit and they're going to have to do a lot of work. In fact, arguably more work than if they weren't trying to make it succinct. So the prover is going to have to do a bunch of work, so just brace yourself for that. But they're doing that work so that the verifier doesn't have to do hardly any work. Okay, and then the second step I'll write right now is we're going to turn the array into a polynomial. Okay, and since I'm writing this stuff out, I'll just let me write it. Then what they're going to do is they're going to commit to the polynomial. And they'll send the commitment to the verifier. Okay, so at the end of this process, the verifier will have a polynomial commitment, so a short commitment value, all right? But this commitment is going to encode the entire circuit and all the inputs of the circuit, all the outputs of the circuit, and every single intermediary value in the circuit. Okay, it's all going to be there in commitment form. Okay, and then what they have to prove then is that this commits to a correct circuit, kind of thing. Okay. All right. The other thing I'm going to assume, I'll write it as step 0 here. Is, and let me actually just move this down. So before we even get started, the verifier needs to, well, it doesn't matter, they can do it after, it doesn't have to strictly be the first step. But at some point, we're going to assume the verifier knows what f is. Okay, so if we go back up here, we have this function. It's not a secret. There's no secret in the function itself. Okay, if there's any secrets, there'll be inputs to the function. But the function is known by the verifier and by the prover. So the verifier knows the circuit here. Okay, so everything that's in blue, they know. All right, if these inputs are public, which we're assuming, they know them as well. Okay, so everything in this picture that's blue, the verifier knows before they even talk to the prover. Okay, so the verifier knows everything in blue. The only thing that they don't know is the things in green. Okay, and they're too lazy to, they could figure out the things in green if they wanted to, because they know all the inputs and they know the function. They're just too lazy, and because the circuit is a million gates big, it takes too long to do that. Okay? So what the prover's doing is they're just proving the stuff in green to a verifier that already knows the circuit, so they know where there's add gates and multiplication gates and how everything is wired up. And the verifier also knows the set of inputs that are public. All right? Okay, so verifier the circuit and any public inputs. Okay, questions about that? You have to have the right mental model. It's going to help. Yeah.
So like the 3, 5, 6, 7, the verifier also does that as well?
Yeah, so we're going to assume that, and this is our simplifying assumption here, where all input values are public. So we're going to assume that they know 3, 5, 6, 7.
Right.
Yeah. So the verifier could compute, we computed 22, the verifier could also compute 22. Again, the only reason we're giving them a proof is because they're too lazy to do it for themselves, okay? Or it's a constrained device, or it's a really big proof, that kind of thing. It's not just the time that it would take, it's also the size. If there's 1 million gates, I have to tell you 1 million intermediary values. That takes a bunch of space, right? And I have to communicate that to you. You have to download it, and then you have to fill all the values in. You have to check all the gates and make sure they're all right, and then you're satisfied at the end. And computers obviously can do things very fast, but there's a lot of scenarios where the circuit here will get so complicated that it's easier to take the proof and consume the proof than it will be to consume all the inputs. Yeah. Okay. All right. So let's go through step 1, 2, and 3, and then we'll talk about step 4. I guess maybe I'll pencil it in here, which is I have to actually prove that it's right. I mean, it's one thing I can load the circuit up into commitment and give it to you, but that doesn't prove that it's right. It just proves that I put some values there, right? And maybe I wrote a 60 instead of a 50. How do you know whether that's right or wrong? Okay, so then I need to actually prove the circuit is right. Okay, the way I turn this into an array is very simple. What I'm going to do is I'm going to first number the gates in the circuit, and the prover and the verifier are going to agree on the numbering. Other than that, it's arbitrary. It doesn't matter how you number the gates, just as long as the prover and the verifier both know clearly which gate is which. So I'm going to call this gate 1. I'll call this gate 2. I'll call this gate 3. I'll call this gate 4. And I'll call this gate 5. All right. Okay, now forget about the whole circuit, just look at gate 1. If I want to tell you about gate 1, what do I need to tell you? Okay, so there's 4 things that you need to know about it. Okay, the first is what kind of gate is it? Is it an addition gate or a multiplication? Because we have both. And then you just need to know the three values, the 2 inputs and the 1 output value. Okay. So what we're going to do is we're going to not put all 4 pieces of information into a single array. What we're going to do is we're going to use 3 arrays basically to grab this information. So the first thing I'm going to do is I'm going to put the values in. So I'm going to say the first 3 values of my array correspond to gate 1. So the verifier also knows this. The first value is a 3, okay? The next input is a 5, and then the output of that gate is an 8. Okay. Then in order to denote whether it's a addition or multiplication gate, I'm going to have a very simple array that's binary, and I'm going to have 1 for all the add gates and 1 for all the multiplication gates. I should note that the way I'm explaining this isn't necessarily the way PLONK is explained in the paper. The way I'm explaining is not strictly the most efficient way of doing it. It's the way that's easiest to understand, and it works. And it's still succinct and things like that. So I'm going to make some simplifying assumptions. But anyways, I'm going to call this polynomial. We'll give names to all these polynomials, but I'm going to call this S for selector, and then I'm just going to put a little plus there to note that it's the selector for all the gates that are addition gates, and this is going to be the selector for all gates that are multiplication gates. Selector vector is always binary, and you put a 1 where you want to select a value, and you put a 0 if you want to ignore the value. So 1 is to select the value, and 0 if you want to sort of ignore it. Okay, now the exact semantics, I'm just going to tell it to you. Later, like before the end of today, you'll see why it needs to be this way, but for now it doesn't really matter why it's this way. Okay, what kind of gate is gate 1? It's addition? Okay, so in the addition selector, I'm going to say it's a 1, and I'm just going to flag the first input of gate 1. Okay, so the first time I hit gate 1, I'll put a 1 there, and then I'll just put in a 0 for the other two values. Okay, is it a multiplication gate? It's not, so I'm going to put all zeros in the multiplication selector. Okay, so this just means that gate 1 is a addition gate. Sometimes we talk about LRO, so that's like left input, right input, output as well. So. Okay, now we're going to keep going. So let's do gate 2. All right, so gate 2, I have an input 6. I have input 7. And I have output 42. Gate 2 is a multiplication gate, so I'm going to put 0, 0, 0 in my addition selector, and I'm going to put 1, 0, 0 in my multiplication selector. Okay, so that means that gate 2 is multiplication. Okay, everyone gets this, right? Okay, so let me, I'll just fill it in more quickly. I won't explain step by step, and then we'll. All right, so we have 8. Keep putting these in green. 8, 42, and 50. Gate 4 is 42, 5, 47. And then gate 5 is 50, 47, and 22. I'll just kind of mark them like this because it's going to get harder to see. Okay. Okay, so gate 3 is an addition gate, so I'm going to put a 1, 0, 0 here, and I'll put a 0, 0, 0 here. The next gate, gate 4, is also addition, so I'm going to put 1, 0, 0, and 0, 0, 0 here. And the last gate is multiplication, so I'm going to put 0, 0, 0 here, and I'm going to put 1, 0, 0. Okay, so look at this, what I've encoded so far, and tell me, is that a complete description of the circuit? In other words, if I didn't give you this circuit, instead I just gave you these 3 vectors and said draw out the circuit, could you draw the circuit out? Would you draw out this exact circuit based on these 3 vectors itself? Okay, so nodding of heads.
So we think of it
here or here?
Yeah,
This is supposed to be a 0. That's just was a little flat. Okay, it's almost a complete encoding of the circuit. There is actually one thing that's missing. Okay, so if you try to encode the circuit and all you had is these 3 things, okay, you didn't know what the circuit looked like. All you have is these 3 vectors. I say go draw the circuit, okay? There's one small thing missing, which is what we call the wiring. So here, gate 1 feeds into gate 3, okay? That's not captured yet, okay? You could kind of guess at it because you say, oh, there's an 8 here and there's an 8 here. So I wonder if the output of this feeds into the input here, but it's not explicitly said, okay? This 8 might have been a public input or something else, okay? So what we don't know yet is we don't know how to wire it up. So we have all of the gates, right? But we're not sure about the wiring, okay? So we're going to need another polynomial that is going to, or another array for now, that's going to define the wiring of the circuit. And this, we're going to worry about later. Okay, we're just going to ignore it for now. Okay, so later we'll talk about it. And it turns out that we can kind of cheat and not actually have a polynomial for doing this. But we'll just, the wiring is actually the hard part of PLONK. So we're about to list out all the things you need to prove that this is right. But the wiring is the one that's going to take 2 lectures to explain. So we'll worry about it later. Okay, so the verifier knows the circuit and any public inputs, so check. We've turned the circuit into an array or a vector or a set of arrays and vectors. Okay, now the next thing we want to do is we want to turn these arrays into polynomials. Why do we want to do that? Well, there's 2 reasons why. One reason is I know how to commit to a polynomial. I don't know how to commit to an array or a vector. If I knew how to commit to an array or a vector, maybe I would do that instead. Okay, so there are actual there's SNARKs that are based on that idea that use what's called a vector commitment instead of a polynomial commitment. Okay, the second thing is I want to get it into a polynomial because it's going to be convenient for me. When it's in a polynomial form, I can do things like add polynomials to each other and multiply them, and that's going to help me later when I want to do step 4, which is prove that the circuit is correct. Okay, so that's why I want it in polynomial form. It's not strictly necessary, you must put it in polynomial form. It's the way that PLONK does it, not the way that other SNARKs do it. Okay, but it's arguably one of the easiest ones to understand. Okay, so we're gonna put it into polynomial form. Okay, so I'm going to we'll just concentrate on how to do it for the first one. And then once we know how to do it for the first one, you do the other ones the exact same way. Okay, so we want to turn this into a polynomial. How would you do it if I told you? You open up the exam and on page 1 it says, here's an array, make it a polynomial. So what does a polynomial look like, just to remind you? It's kind of like C0 plus C1x plus C2x squared. So what I want to do is I want to take these values and I want to stick them in the polynomial somewhere. And now that polynomial represents these values. Okay, so where can I take these values and stick them into the polynomial? Okay, so there's a couple options that I have, and the most obvious one is what if I just put them in as the coefficients? So C0 is 3, C1 is 5, C2 is 8. Okay. so method 1, program into coefficients. So 3 plus 5x plus 8x squared plus 6x cubed, et cetera, et cetera. Okay. How easy is it to, let's say I want, this is sort of a dumb question, but let's say I want the polynomial and I want it in coefficient form. I want it in coefficient form because the next step I want to do is I want to commit to it. So I'm going to commit to it using KZG. I need to know the coefficients anyways. Okay. So if I program my array directly into the coefficients, do I have to do anything to get the polynomial in coefficient form? I don't, it's already in coefficient form. Okay, so it's in coefficient form. So if I do this method, it's going to be very, very fast to commit to. I don't have to interpolate it, for example, first. This has some other nice properties. For example, let's say I have two polynomials and I add them together. What happens? The coefficients add together as well. And so I get the addition of the two coefficients with each other. Okay, so coefficients. So if I have, say, polynomial 1, and I add it to polynomial 2, this is basically the same as, my notation here is not great. I should have worked this out ahead of time, but I'll write it in English. So sum of two arrays, let's say I have two arrays, I want to add them together, can be done by the sum of the two polynomials that represent them. Okay. What about multiplication? Let's say that I have two arrays and I want to multiply them together. So I want to create a third array, that's the multiplication of them. Can I just multiply the two polynomials together and it will give me the same thing? So it won't, and why not? Okay, so I'm going to have to do this big cross product, right? And so I'm not going to get multiplication. So multiplication won't work the same way. So I'll say multiplication of arrays not possible from multiplication of the polynomials. So the easiest thing is to see an example. So let's say that we have an array 6, 7, 8, and I have array 1, 2, 3. Okay, and I want to multiply the two together. So that's going to give me the array 6, 14, 16, 24. Okay, all right. So this is on the array side, okay? On the polynomial side, I'm going to have 6 plus 7x plus 8x squared, yeah? I'm going to multiply it by 1 plus 2x plus 3x squared. Yeah, you see it now? And so, yeah, so I'm going to get 6. I'm basically going to get the cross product of all of these things. And the whole degree of the polynomial is going to be way bigger than 2 anyway, so it's not going to give me what I want. Yeah. I'll just write cross product. Okay. What if I want to open up the 6th element of the polynomial, or let's say the 4th? So I'm like, okay, the 4th thing in my array is a 6. I'm not going to show you the whole array. I just want to prove to you that 6 is correct. Okay? Can I somehow just, without telling you the whole polynomial, can I say the 4th coefficient is a 6? So it turns out you can't. You might not know whether the answer is right or wrong, but there's no like real like mathematical way of just selectively revealing one coefficient. Okay? So we can't selectively reveal one coefficient. Okay? And another way of thinking about this is that let's say we have the array and we want to encode it into a polynomial. That is very fast. But let's say we want to do the opposite. We have the polynomial and we want to dump it back to the array. Then it's not fast. Okay, so it's not. So say it louder, that we just need coefficients to. So what I'm saying is, let's say I write down this polynomial, but it has 1,000,000 coefficients. And let's say I commit to it with KZG, so I give it to you. Now I want to just prove to you that the 4th coefficient is 6, but I don't want to show you all of the polynomial, right? So there's no easy way for you to check just that one coefficient. There's nothing I can like add to it or multiply it by or divide it by in order to isolate that one coefficient and prove it to you. Yeah? So think about why that's the case. It's hard to improve. It's easy to show you, like if something is possible, I can show you why it's possible. If something's impossible, I can't show you why it's impossible other than nothing that you try will work in the end. So. Exactly, so that's the right idea, right? So think about that. So all I'm telling you is 6. So you can make a degree 4 polynomial with 6, or sorry, degree 3 with a 6. But there's nothing you're going to do to this polynomial without looking at every coefficient that's going to help you like determine that that was actually a 6 or not. Yeah? Okay, okay. Okay, the second thing, okay, so this is fine. So programming into coefficients, it's really fast when you want to go in one direction, but if you want to go backwards, it doesn't work so well. And you don't get this adding and multiplication property, okay? We will use this, okay? So in PLONK, at a certain point, we're going to program things into coefficients because it's the fastest way to do it, and we never have to go backwards. We're just doing it in one direction and we're not coming back. Okay, but for what we're doing right now, which is programming the main circuit trace, we're not going to use that approach for that purpose yet. Okay, we're going to use a different approach. Is there anywhere else you could take these arrays and stuff them into a polynomial other than the coefficients? So I want a polynomial that represents these values, all of these values. Okay, so can you give me a polynomial where all those values are somewhere inside the polynomial? Okay, so there might be another way of encoding into the coefficients other than directly. like sort of indirectly encoding it. That's not the approach at all. Okay, what we're going to do is we're literally going to put those values in. We're not necessarily, you don't have to put it into this equation, right? Just don't get married to this equation. Just think about what a polynomial looks like. You got to put the points somewhere in that polynomial. Okay, so we can program it into the points of the polynomial itself. Okay, so what I can do is I can so what I do is I pick a set of x values. We call this the domain of the polynomial. So probably the simplest domain is just 0, 1, 2, 3, 4, etc. And then if the first element of my array is 3, then I put a point here at 3. And then my next one is 5. So I put a point here at 5. Then I put a point at 8. Then 6. And a point at 7. And keep going. And then what I do is I interpolate those points to give me a polynomial that runs through those points. Okay? And so this is a polynomial. It encodes all of the values themselves.
Sorry to get back to something before.
Yeah.
Why is it not fast to go from a polynomial to an array?
I can't explain why. Just try to do it yourself, and you'll see that like probably whatever idea you have doesn't work in the end. It's sort of like proving an impossibility. It's hard to prove why it's not possible. Other than just like whatever little idea you have probably won't work if you just think about it for 5 minutes. Yeah. Okay, so we can program it into the points of the polynomial. We have a domain, okay? And what we can do is we can get fancy with our domain. So here, let's say I want to go from, say I'm at this point here, and I want to go to the next value. Okay, so I'm at p of 3, and I kind of want to go up a value. Then what I'll do is I'll go to p of 4, right? I'll go to p of 3 plus 1 equals p of 4, okay? So that's how I like sort of advance through all the points along the polynomial, okay? For reasons that will be very convenient that we've already seen, but we didn't really see why they're useful, what we want to do instead is if I'm sitting at a value, when I advance, what I want to do is I want to multiply it by something instead, okay? So the value that we'll use to space out the points we're going to call omega. So if I'm sitting at some value, say a, to get to the next value, I'm going to multiply by omega, and that's where my next value is going to be. Then I'm going to multiply it by omega again, and then eventually what's going to happen is I'm going to loop and go back to where I started. Okay. So the way we encode it, everything will be a power of omega. So what I'll do is I'll find this omega value, and I'll program my first point at that value.
So we are not doing 0, 1, 2, 3, 4 like this?
Exactly. Yeah. So what we'll do is we'll program them at these omega values instead. I'll show you what the omega values look like and how they work. Later, we don't need it for now. If this confuses you, you can continue to think of programming them at 0, 1, 2, 3, 4. And the PLONK, you could actually do it this way. It works fine. It's just that there's one little step that is going to be in like 2 weeks where we're going to use the property that it wraps back together. That's the only time that you strictly need it. And even then, you don't strictly need it. There's another way to like accommodate for the fact that it doesn't wrap around. Yeah. The other thing is that this will be a lot faster because we can do fast Fourier transform for interpolation. But anyway, these things don't really matter. Okay, so what I'll do is I'll program the first value at 3. Then what I'm going to do is I'm going to find omega squared, so it could be anywhere along the line. It doesn't, because it's mod, it doesn't necessarily go up. So I'll find omega squared. Then I'll program the next value, which is a 5. Then I'll multiply omega squared by omega. That will give me omega cubed. Say we wrap back to here. And then I'll program the next value, which is 8. Then omega 4 is 6. This isn't really drawn to scale. And then
Sorry, are square and cube inverted?
first, sorry, just let me fix one thing before I answer your question because I made a mistake here. Not a mistake, but it's easier to start from 0 instead of starting from 1. So the first one will actually program. Let me draw it here explicitly. Omega to the 0, which is the same as 1. So we'll program the 3 here. And then we'll go to omega to the 1. Then we'll go to omega to the 2. Then we'll go to omega to the 3. Then we'll go to omega to the 4, which is 7. Okay, what was your question? Sorry, if that didn't resolve it.
Well, I'm not sure I'm getting the whole deal here. It seems like
Okay. Let me just wrap this up, and then I'll come back. I'm going to circle back to this in a sec. Okay. Okay. So what I do is I interpolate a polynomial through this. Okay. And this is now my polynomial. Okay. So let's talk about this omega and where it comes from. So I'll just put a side note here.
How are we taking this number 37856?
Sorry, say again.
35876.
Did I do it wrong?
378.
8, 6, 7.
But it's like, why does omega, like, as you increase the power, why is it going back and forth?
Okay. So I didn't explain this. I actually explained it like many slides ago, but let me just drill in on this itself. So this, for example, we call it roots of unity. So it's here. And I didn't motivate really why we want it like this. So let me go down here. Something we can also like defer for later because we don't actually really need it right away. It's easier to like explain it the right way at first instead of like swapping things out later. So hopefully this explanation is clear. So let's start with the simplest domain. Let's talk about 3 possible domains that you might use. The first thing I want to note is that the domain is completely your choice. Okay, you can encode the polynomial as long as the prover and the verifier they both agree on what the domain is. It doesn't matter. So if there's some domain that's more convenient for whatever reason, you can use it. Okay, so there's no rule about why you have to use a certain domain. The reason that we're using this domain is just because it's more convenient. Okay, why it's more convenient? It's going to let you interpolate faster. You can use fast Fourier transform. And it's also going to have this wraparound property that I'll try to explain now. Okay, so let's say we do a normal domain. So a normal domain would be 0, 1, 2, 3, 4, 5, 6, 7. Okay, up to like 100,000 or a million or however big your polynomial is. Okay, so let's say I want to go from the first point to the second point. What do I do? It's a dumb question, but what do? I add 1. And then if I want to go here, I add 1. And then if I want to go to the next one, I add 1. Okay? What happens when I hit 7 and I add 1 to it? I'm going to go to 8, right? But 8 isn't it's not in my domain. Okay, so my polynomial doesn't, remember the number of x values here is q. That's a huge prime number. I have a big circuit. I have 1 million, my polynomial size 1 million, but 1 million is really, really small for q. Okay, so I'm not using all the points that are available to me. I'm actually using a very, very, very small fraction. Okay, so if you want to visualize it more like just without the polynomial, you can think of this is a number line between 0 and q, and my domain is like, it's way smaller than this. It's like actually like like you couldn't even see it. Like it would be smaller than a grain of sand if you could visualize it. But the point is that my domain is right here at the start of the line, okay, and then I have all this empty space here, okay. And once I hit the last element of the domain, I'm going to bounce out of the domain. Okay, if I keep adding 1 to it, I'm going to bounce out of the domain. Okay, now my next idea is I don't want to bounce out of the domain. What I want to do is I want to always stay in the domain. Okay, so the next idea I have is what if I space out these numbers? Okay, so for example, I start at 1. That's fine. So I encode, or 0. Okay, then I move over some step, we'll call it like alpha. So if I want to go to the next one, I go from 0, I add alpha to it, then I'm in my next element, okay? Then I move over another alpha, and then I'm here. Then I move over another alpha, and so I have a point here, okay? And then what I really, really want is I'm going to have my last point, okay? And if I move over alpha from my last point, I'm going to wrap around and I'm going to come back to the first point where I started. Okay? So I have this alpha value, I keep moving over, okay? And then the last one, when I add alpha, I go back to the start, okay? Then it's closed under addition. How do I figure out what that value of alpha is that would let me space it out like that? So I know how big my domain is. Like I know that I have 8 values that I want to program. Okay. So what I want to do is I want to take the number, the size of this, and I want to partition it into 8 equal sections. Otherwise, I want to divide by 8. Okay. I just want to divide it by 8, and that will tell me the jump size. Okay? All right. There's one problem. How many values do we have along here? We have q values. What is q? What kind of number is q? It's a prime number. What's a prime number divided by 8? Is it an integer? Strictly, right? A definite, what does it mean to be prime? It means there's no divisors of it, okay? So there's, once I say there's q elements, there's no possible way I can divide them into q, or into sets of alpha that are the same size. I just can't evenly divide, okay? So this approach will just never work. It's a dead end because q is prime, okay? So my next idea is, what if I use multiplication instead? Okay, so what I'm going to do is I'm going to pick my first value. I'll start at 1. Then I'm going to find my next value, which is omega. So I get from 1 to omega just by multiplying by omega. Then I multiply omega by omega, so I get omega squared. Okay, then I multiply by omega again, so I get omega cubed. And this was the question of back to like, why are these all out of order? Why is it omega 0, 4, 2, 1, 3? Well, when you multiply things, you're gonna go past Q pretty quick. And when you go past Q, it's going to wrap because it's a modular kind of thing, okay? So when I go from W squared, I'm going to wrap around maybe a couple times, and then I might end up, you could end up anywhere on the number line. So maybe omega cube ends up here. Then I multiply by omega again. I wrap around a bunch of times, and then I end up here, okay?
We are taking mod.
Yeah, because we're taking mod. Yeah, so everything is mod Q, okay? Then, is it possible that I start at omega 4, I multiply by omega, I wrap around a bunch of times because it's mod, and I end up back where I started. Okay? So what I need is I need an omega that divides, not subtracts, but it divides the order of Q. Okay? The order of Q is Q minus 1. Q minus 1 is divisible. Okay, so if I can find an omega value that divides Q minus 1, whatever Q minus 1 is, then I can set this up where I basically, if I want to move to the next element in the polynomial, I just multiply by omega. And then eventually, when I hit the last element, if I multiply by omega again, I go back to the start. So I loop. Okay, and because of this like looping, or it's closed under multiplication, that's what makes fast Fourier transform possible and a bunch of other stuff. So there's a bunch of consequences to it, okay? Why this works, you can go back to the lecture we gave a while ago where we talked about like orders and things like that. Just accept it is what I would say, okay? So we're gonna have this value omega and it's gonna work this way and you're just going to accept that it works this way and not worry too much about it. Okay. When NIST chooses elliptic curves, they choose them on purpose so that Q minus 1 has lots of values of omega that allow you to do this. Okay. So there's lots of numbers there that you can work from. Okay. So we're going to do this approach, but yeah. Okay. Let's just move on now. Okay, so we want to program into the points of the polynomial. So I want to kind of model this. So the first comment I made was how fast is it? Then I talked about adding things together. Then I talked about multiplying things together. And then we talked about selectively revealing. So let's think about those 4 things for this approach. So first off, how fast is it to get into coefficient form? Okay, so I have 3, 7, 8, 5, 6. I know the values of omega. Okay. So I want to put that into coefficient form. I can draw it out with the x values here. So I have an array, it kind of looks like this. So this is the domain. And then this is the array values just that we had before, 3, 5, 8, 6. I want to turn this into a polynomial where I know the coefficients. What do I have to do in order to turn this into coefficient form? So I have a bunch of points on the domain. So I know a bunch of points. I need to draw the line through the points, right? And then write down what the coefficients are. Yeah.
I think W squared is 8 and W cubed is 6.
Sorry, say again. The
W squared is 8 and W cubed is 6 inverted there.
maybe
3, 5, 8, 6, 7.
3, 5, 8, 6. 3, 5, 6, 8. So then maybe the diagram is wrong. So that's 2 and that's 3. Yeah. Sorry, yeah. Which side of which? What do you mean by which side? Sorry, I didn't quite get.
One there and two on the right.
Oh, I just made that up. I just made that up. Yeah, like I have no idea for this particular value of omega. I don't know. But the point is that they won't be in order. They're going to be out of order. That was yeah. I just made it up. Yeah. Yeah.
So if you had just arbitrary word, you would.
Exactly. Exactly. Yeah. Okay. How do I have a set of points. I want to turn it into a polynomial. How do I do it?
We take the point and a y and then just multiply it.
Okay, so I can't do multiplication. I wish it was that easy. It won't work. I have to do something stronger. Interpolation. Okay, so from a speed perspective, would I rather program into coefficients or would I rather program into points? If speed's my only concern, I'd rather program into coefficients because I don't have to do interpolation. Okay, if I program into points, I have to do interpolation. It's like n log n, or d log d for the degree of the polynomial. Work? Or it would be d squared if we use the domain like this. If we use 0, 1, 2, 3, 4, it would be d squared work. Because we have this root of unity, we can do it in d log d. We can use fast Fourier transform. But anyways, the point is I have to do some work to get it into coefficient form. Okay? So that's a negative of doing this approach. Okay? There are positives. So the first is, let's say I have two arrays and I want to add them. If I make polynomials out of those arrays, and I make the polynomials on the same domain, okay, then the resulting, if I add the two polynomials together, that will give me the same results. Okay, so if I have let me just do a simple example here. 1, 2, 3, 6, 7, 8. So we can call this array A, and this is array B, and A plus B is going to be 7, 9, 11. So forget about circuits for now. Just think of in general of arrays. Yeah, we'll put it back in circuit terms in a second. Yeah. Okay, so if I have two arrays and I add them together, that's the same as adding the polynomials. Okay. So here's omega to the 0. So in one polynomial I have a 1. In the other polynomial I have a 6. Here's omega to the 1. And I'll put omega squared here. So here I have a 2. Here I have a 7. And here I have a 3. And here I have an 8. So this is polynomial A. This is polynomial B. If I add them together, what's 1 plus 6? Well, it's 7. Okay, so my polynomial will be just the sum of what it is at each point. 2 plus 7 is 9, and 3 plus 8 is 11, and so I'll get polynomial A plus B. Okay, so if I add them together as polynomials, I get the sum at every point, and if I add the arrays together, I get the sum at every element of the array. So they're homomorphic, if you want, between the array form and the polynomial form. Okay. And I won't go through the same exercise, but if you multiply instead, okay, the multiplication of a polynomial at a certain point is the multiplication as well. Okay, so multiplication also works the same way. So every now and then we're going to want to multiply arrays with each other. Then if we have them in polynomial form, we just multiply the polynomials, and it is the same. Okay, the third thing is, can I selectively reveal? So can I open up the polynomial? Say you care about what's the polynomial at omega squared. Can I just open that one point up on the polynomial? So I can. So with KZG, we saw how to just open a single point on the polynomial. Okay, so I can. So I can open just one point. Okay, so we like this better for what we want to do for PLONK because we can do, we're going to use this property a lot. We're basically going to use this property all the time. And the addition and multiplication is also very convenient. Okay, so what we're going to do is we're going to use this approach when we encode the circuits. Like I mentioned, we will use this in one small case. And there's a third thing that we can do that I'll just say very quickly, I won't write out a lot about, that we also do in one specific case, but we don't generally do it, which is we can program the array into the roots of the polynomial. Okay, so what that means visually is 3, 5, 8, 6 are all roots of the polynomial. That means they cross the x-axis at those values. So 3, 5, 8, 6, 8, etc. They're all roots of the polynomial. So that means it's kind of like having a set of points, but they're special points because they're all at 0. Okay, and so when you draw a polynomial through it, it's going to cross the 0 at all the points in the array. Okay, now this turns out to first off, it's like interpolation where you have to turn it into coefficient form, you have to use this formula. So you have, sorry, you don't have to use this, there's faster ways of doing it, but it's an easy way to understand how to do it. So you're going to do long multiplication. So every time you add another term, you have to multiply it by all the existing terms. So this ends up being like ON squared. The big problem with this approach is, let's say I have this array, 3, 5, 8, 6, 7. I have almost the exact same array. I want to commit to it using roots. The only difference is that the 8 is here and the 5 is here. Okay, so it's the same array, but it's in a different order. All right? What will happen is I'll end up with the same polynomial because there's no order here. Okay? Notice here, if I swap the order, I get a different polynomial. Like it goes up first before going down, or it goes down. So when I order, when I commit to, if I change the order without changing what I'm committing to, I always get a completely different polynomial. Same with the coefficients. So if I swap the 5 and the 8 here, it's a different polynomial, even though they look the same. Okay? But if I encode in the roots, then it doesn't, order basically doesn't matter. So order, okay? And so this is either a good thing or a bad thing. It's usually a bad thing because we want to not just commit to data, we want to commit to the order that they're in, okay? But it could be a good thing if we don't care about that, okay? And so what we're going to do is, eventually down the line is, I'm going to prove to you that one array is a shuffle of another array. It has all the exact same numbers, the order has been changed. I'm going to use this way of encoding it into a root because when I encode the shuffled version and the unshuffled version, they'll result in the same polynomial. And then I'm going to prove to you that they result in the same value polynomial, okay? So generally they're bad, but they could be good if, for like proving shuffles. That's like basically the only way that they're good. Shuffles are important in PLONK, so the P in PLONK is permutation, and permutation is another fancy word for shuffle. And so it's going to show up like a little bit later, but for now we can just sort of set this aside. Okay, so I know we're going to take a break in a second here, but I'll just say that, so you know the circuit and the public inputs. We turn the circuit into an array, okay? That was just encoding the gates one by one. Then we can turn the array, in this case the 3 arrays, into a polynomial, okay? And the way that we're going to do it for now, until we need to do it another way, is we're going to do it by programming it into the points of the polynomial, okay? So we put the values as points, we draw a line through it, now that's a polynomial, and we can commit to that polynomial using KZG, and we can send the commitment to the verifier, okay? So this, we just use KZG, we already saw that last lecture, or last couple lectures, and so now the verifier they're holding 3 commitments, okay? They have a commitment to this array, they have a commitment to this array, and they have a commitment to this array. And that's the 3 things they're holding in their hand. And then now we have to do the hard part of proving that this was filled out correctly, basically. Yeah.
So like for each of the arrays, we have like a separate polynomial that we send?
Yeah, so for every array, we'll send a separate polynomial. Yeah, so there are ways of doing that. And again, PLONK actually, they send one polynomial for all the L values, one for all the R, and one for all the outputs. We're collapsing them into one. Here, because there's only addition and multiplication, as soon as I see 3 zeros, I know it's not multiplication, therefore it is addition. So like these 2 could also get collapsed into 1. Like you could just encode a 0 or encode a 1. Yeah, for each operation. Or you could use 1 and -1 or something like that. So there are ways of making this more polynomials or less polynomials, but this is a nice way that's, I think, easiest to understand is just by arranging it like this. Yeah, but yeah. And also the other thing I would note is that the verifier knows these 2 before you start. They know what the circuit looks like, so they know these 2 polynomials, okay? So they could have pre-committed those 5 years ago. They just don't know this polynomial because this polynomial has all the values in it itself, yeah? So these are, we call them helper polynomials because you can pre-compute them. That's what, yeah. The which? Yeah, so the wiring of the polynomial we haven't talked about yet. You can think of it as it's going to be a polynomial, yeah. But it's going to be like, it's too hard to explain now. It has to do with shuffles, actually. So what you're doing is you're writing down all the wires. You're going to number all the wires. You're going to write them down in order. And then if 2 wires are the same, you're going to shuffle the locations of the places where the 2 wires are the same. So that's what this polynomial will be, is basically, so it will be one polynomial. It'll be kind of like the numbers 1 to the 3 times the number of gates that you have, so 1 to 15. But there'll be little shuffles inside of it that denote that 2 wires are the same. Yeah. Sorry? Yeah, please, yeah. So let's come back in 10 minutes.
You can read something, you can tell it's like generated like
Okay, we'll start again. Okay, so let's go back to our list here. So we assume the verifier knows the circuit, all right? And basically what that means is that they know S plus and X, and then whatever we talk about wiring later, they also know. That's what it means to really know the circuit, is that they have these values, okay? They also know that like which gate is G1, which gate is G2. That's not really encoded directly into the polynomial, but it's just, we consider it common knowledge between the 2 itself, okay? The verifier doesn't necessarily need to know it before. So like, let's say that there's a SNARK and you want to verify it. It's not like you had to know what the circuit was before. You'll just go to the website that has the SNARK proof, and then they'll say, here's the circuit, and then you'll get it, and then you'll check it, and then you'll verify the SNARK itself. Okay? Yeah.
So there are only two inputs for the circuit, right? I mean, the other circuit that
Two inputs
I want
to the circuit or to the SNARK?
to each of those small signals.
Yes, correct. Yes. So so these are gates, and we assume they're binary gates. Yeah, strictly. Yeah. So and that gives us structure. So this polynomial will always be 3 values, 3 values, 3 values, and it will always have the same structure. There are ways of doing gates that are not binary, like where there's one input and one output, like a lookup, and PLONK supports that, but that's like an advanced topic. So for this course, we'll just assume, yeah.
Basically,
Is which, sorry?
reduced instruction versus complex instruction. It would be harder to put, right?
Yeah. So you can, if you make the gates more advanced, you can reduce the number of gates that you need in your circuit overall, which makes it more efficient for the prover to prove. Yeah. Okay. So we have this. Okay. All right. So let me go back to this list. Okay. So we know the circuit and any public inputs. Okay. So what does it mean to know the circuit? It kind of means you know S plus, you know S minus, you know the order of the gates, etc. We turn the circuit into an array or vector. So this is how I'm choosing to do it. Again, it's not the only way of doing it, but it's a sufficient way that's easy to follow, hopefully. You turn the array into a polynomial. So here, what we're going to do is we're going to use evaluation points. We commit to the polynomial and send the commitment to the verifier. Here, we're going to use KZG. Okay. You don't have to use KZG. There's other polynomial commitments. The main alternative to KZG would be if you care about quantum computing. So if you're like, oh, quantum computers are a big threat, I want to do something that's post-quantum, then you're going to use something instead, probably called deep fry, but there's other ones as well. Okay, then we want to prove that the circuit is correct. Okay, so the verifier now has a commitment. They know S plus and XX, but they can hold them as commitments if they want. And you give them a commitment to this trace of the circuit. Okay, so the verifier at the end of this, they hold this. But is this array correct or not? Okay, the verifier doesn't know, right? I could, like if I replace this 42 with 47, it's no longer a correct circuit trace, but it's still a commitment to a polynomial, blah, blah, blah. You know, it still has 3, it's structured correctly and things like that. So I have to prove that this is right, that this is a correct circuit, okay? So that's going to be, as you imagine, the hard part. Okay. All right, so here, so the prover will make the circuit trace.
Verifier gets the array as well.
Yes, yeah, but what does that mean?
Do verifier just get the polynomial or the array and the polynomial?
So the verifier, let me go back. The verifier only has one thing, which is a commitment to the polynomial of the array. Yeah, that's all they have. So they actually don't know the polynomial themselves. This is important to understand. They don't know the full polynomial, and they don't know the full array either. Yeah, and they could know those things if there's no secrets involved. It's just that they're too big. Like it's a million coefficients and they raise a million things. That's the only reason why. Yeah? Okay. All right. Okay, so the protocol so far is, I'm just going to rewrite out the steps that we had before. So the prover and verifier agree on the circuit, S plus, S multiplication, etc. I won't write all the details, but they agree on that. Okay. The prover encodes the circuit into an array. Prover encodes the array into a polynomial. So we have the circuit, then we go to an array, then we take the array, we go to a polynomial, and then we take the polynomial and we go to a commitment to the polynomial. Okay? And then now the prover wants to convince the verifier that the polynomial is correct, is a correct circuit. I'll call it a trace. A trace just means that you trace through all the values in the circuit and you write them all down. And so that's what we want to prove. Okay, so this corresponds to these 4 steps. And in order to help me, I'm going to just make another copy of this. Okay, so the question is how? How do I convince you that this is correct? Or better yet, forget about how is hard, but like what do I need to convince you of? Okay, I tell you that this is right. This is a correct trace of this circuit. Okay, what does that mean for it to be correct? Okay. Yeah, so something about the order is correct. Okay, so we're going to break it down. So there's going to be a couple things that you need to prove. What are some other things that I could prove to you? Even if you look at these numbers, what do I need to prove about these numbers? For example, this number 8, right? Why is 8 the right number to stick here?
So that you can do the correct operation.
Okay, so 8 is 3 plus 5, yeah? So I need to prove that the correct operation or the correct gate was correct. So I can do that for all the add gates, I can do it for all the multiply gates, okay? I came to you at the start and I said, if I execute this circuit on the inputs 3, 6, 7, you get the output 22, okay? How do you know I actually use 3, 5, 6, 7? You don't until you go looking for it, okay? How do I tell you the output's 22? How do you know the output's 22? Well, you have to go and you have to look here, okay? So to prove that this circuit is correct, we basically are going to do 5 things. We're going to open up all the inputs and show the verifier that those inputs are what they think they are. We're going to open up the output and show that the output is what it should be. We're going to prove all the gates are done correctly, all the addition gates and all the multiplication, we'll do it as 2 steps. And then finally, we're going to prove that the ordering or the wiring is done correctly. Okay? Yep.
But Professor, 3, 5, 6, 7 are the public inputs, right?
Yep, 3, 5, 6, 7 are public. But so the verifier knows 3, 5, 6, 7, but do they know that you actually use 3, 5, 6, 7 when you made this array? Yeah? So I can tell you the public input is 6, but then here instead of putting a 6, I put an 8. Because the 8 is the right thing that will give me the answer 22. So I lie to you about it, kind of thing. Yeah? So it's they are public so they can know it. It's just you have to prove that you actually use them. Does that make sense? Okay. All right. So we want to prove, so step 4 was prove trace is correct. And we're going to do it in 5 steps. Okay? So I'm going to prove that the public inputs are correct. I'm going to prove that the output, the public output, is correct. By correct here, I don't mean that it's computed correctly necessarily, I just mean that it shows up in the right spot. I'm going to prove that the all add gates are correct. I'm going to prove that all mult gates are correct. And last, I'm going to prove that the wiring is correct. Okay, so these are the 5 things this is what we need to do, and when we're done this, we're done PLONK. Okay, now you've seen a SNARK. Okay, this is very easy. This is very easy. You should already be able to tell me how to do it. This is like relatively easy, but you have to think about it. You don't know the answer quite yet. I'll put medium. And this is very, very hard. Okay, so this I can tell you in 5 minutes. This I can show you before the end of the lecture, and this is going to take 2 lectures to explain, at least. Okay, but anyways, that's just so that you sort of brace yourself for what's coming. Okay, so that's why I'm sort of pushing the wiring off. But for now, let's try and prove these first 4 properties. Then we'll worry about the wiring later. We'll save that for another day. Okay, let's do just one version of the first one. So I want to prove that public inputs are correct. Okay, let's take 5. 5 is a public input. Okay. So we'll start with 4A, public inputs. And I want to summarize what the verifier knows. Okay, and it's probably about time that we label this. So I'm going to call this C for circuit. I think that's fine. So we'll call this the circuit polynomial here. Okay, so the verifier knows a commitment to the polynomial of C. The verifier knows S plus and S multiply. And the verifier knows, I'll call it the layout of the circuit, which is basically the order, what gate, like, which gate are we calling gate 1? So I called this one gate 1, this one gate 2, gate 3, gate 4, they know that. Okay. I'll put order of gates.
But this is equivalent to knowing S plus and S small, right?
Sort of, so it's this, let me put it like this. This implies this. So once you know this, then you know this. But it's not, you can't get the layout from this, right? Like this just tells you There's the first gate's a multiplication gate, but it could be this multiplication gate or this multiplication gate. That makes sense? Yeah.
What's the format of the layout and how do you?
So I denoted it as G1, but it's not in the data structures themselves. So it's, you can think of it as meta information, metadata. So it's just sort of like, it's something that's not, it's not being passed around. It's just something that they understand. Yeah? Okay. Technically, I guess, once you have the wiring vector, then that will, S plus SX plus the wiring will actually tell you the layout of the circuit. So that would be sufficient itself. But yeah. Okay, let's say I want to check that 5 is correct. All right? How do I check that 5 is correct? So the verifier says I use 5 as this input to the circuit. Okay? I want to make sure that 5 ends up in the right place here. Okay? So where do I check? What do I have to check about C to know that 5 is, when the verifier did this trace, and they say that they're using 5 here, that they're actually using 5 here. So I'd say, well, 5 is the right input to G1. Okay? So 5, so I'll write example here. Input 5. Okay. So input 5 is the it was the right? Right input in G1. And we also know that it's the right input to G4. Right? Right? So the right input in G1 better be a 5, and the right input in G4 better be a 5. Okay? Can I find where that is in the array? Right, I can. So I know that G1 is going to be, let's index from 0, so it's going to be in 0, 1, 2, and then 3, 4, 5, 6, 7, 8. So I know that G1, and I know it's always LRO, LRO, LRO. Okay? So I'm able to locate, I know already like where it should be. It should be the second position in the array, and it should also show up in the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? If you want to get mathematical, you can use mod 3. So you can say left is 1 mod 3. So you can do 1 times 3. And then, though I should actually label them gate 0. I should have said this was 0 and said 1 for that to work. But there is a mathematical way of you do 1 times 3 plus 1 because it's the right input. But then it's going to be off by 3 because I didn't index from 0. But anyways, the point is the verifier knows where these are. So they know that it's going to be at C of 1, and there better be a 5 at C of, I already forgot what I said, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so input 5 better be, if I evaluate the polynomial C at 1, I should get 5. And if I evaluate the polynomial C at 10, then I should get 5 as well. Okay? Can I verify that if I have a commitment to the polynomial C? So I don't have C itself, I just have a commitment to C. Is there a way that I could learn that the value at 1 that's committed to is 5? Or the value at 10 is 5? So again, I'm the verifier in this scenario. I can't check the array because I'm too lazy. The array is 1 million elements long. And you might say, well, all the inputs are at the start, but in this case, like one of the inputs was way at the end, right? So I'm too lazy to check the array. Okay. I have a commitment to the array. So I have the array in polynomial form committed, right? So I have C, it's committed to. So I'm holding the commitment. What can the prover do?
Check at omega 1.
Sure, but yeah, but more broadly, what they could do is just open it up at that point. Can KZG prove to you what a point is along a polynomial without telling you the whole polynomial? It can. That's the defining feature of KZG. Okay. So what I'll do is I'll have a commitment. I'll write KZG here. Okay. So what the prover will do is they will just run KZG selective reveal or open. And they'll give you a proof that C of 1 equals 5. And then you'll run it again, and you'll get a proof that C of 10 equals 5 as well. Okay? If you want to get, so basically for every public input, you'll do a KZG opening. Not just every input and every place that input is used. Okay, so I'll do one opening on 3, I'll do the opening on 5, I'll do the opening on 6, and I'll do the opening on 7. 5 here should be in blue using the colors that we're using before because it's a public input. Whoops, 5. And so I'll just open it up. Now with KZG, there is a fancy batch opening where if I want to open a bunch of points on the same polynomial, I can actually do it a lot quicker than just opening them up one by one. But for the purposes of this course, just assume that you open them one by one. Okay? So the main thing is that the verifier can find where the public inputs should be in this array. And then the prover can just open them up using KZG. Okay? So that's how we satisfy that the public inputs are correct. For public outputs, it's the exact same thing. I figure out where is it. So it's the output of G5. So I find where G5 is. I find where the output of G5 is. Okay? It's probably going to be the last thing in my array, but if I number the gates weird, maybe it's not. And then I ask the prover to open up that value. Okay? Open it up, show me that it's a 22 there.
We are verifying both the array and the polynomial.
Sorry, say again.
So we are verifying both array and the polynomial, like the prover is doing it here.
Yep. So the array is kind of think of it as like a helper value for the prover themselves. So they take the circuit, they put it in an array, then they put it into a polynomial. But the polynomial is the array. It's not, they're not like two separate things. The array was just sort of the helper to get you into the polynomial. But technically what they're doing is they're just proving to you about the polynomial.
So if we have input 5, so we need to go through all the numbers to see whether where that 5 is.
Yep. So look at the circuit visually. We have the public inputs at the start. Every gate that a public input goes into, you do have to check that value. Yeah, so for every time you have a public value, you have to figure out what gate it's going into, what input it is. You're going to have to check all of those. Yeah, but most of the circuit, this is sort of an unrealistic example, but most of the circuit, like the inputs are going to be at the top level, but the circuit's going to be really deep. And so the number of inputs are usually small compared to the size of the circuit itself. Yeah. Okay, so I'm simply going to open up all the points here. So this is easy. I'll just open with KZG. And for the output, I do the same thing. Okay, it's the same procedure. I'm looking at a different location. Okay, so we're 2/5 of the way for proving PLONK. Now let's think about the addition gates. So what I want to do is I want to prove that every add gate in C, where C is a polynomial, the verifier doesn't have the polynomial, they just have a commitment to it, but C is the encoding of the trace. I can also include S plus because I'll need it. I'll put S multiplied here, although I won't need it for now. I want to prove that every add gate in C is correct. Okay, show me visually, what does it mean for an addition gate to be correct? First off, where are the addition gates? Okay, so every time in this array where I have 1, 0, 0, that's where I have an addition gate. Okay, so this is an addition gate, and this is an addition gate. And the one right after, thank you. So I have 3 addition gates, okay? So I want to care that these 3 values are correct, as according to addition. These 3 values are correct, and these 3 values are correct. Do I care about anything that's going on anywhere else? Not now, okay? Later when we do multiplication, I'll care about it, but for now I don't care about any of those, okay? Is there a way that I could ignore these values? Actually, put a pin in that. Forget about that. That's the harder of the 2 questions. What does it mean? Just look at these 3 values here. Okay? What does it mean for addition to be correct? Okay, so the output is the sum of the previous 2 numbers. And notice I said previous 2 numbers. Okay? So I have a number, think of an index, a pointer. I'm going to point my pointer here, and then I'm going to move over 1. I'm going to grab that number, and then I'm going to move over 1 and grab that number, and then I'm going to say that I plus 1 equals I plus 2. Does that make sense? Okay, but the way we move over is going to be a little different because we're using these roots of unity. It's the same thing here, and it's the same thing here. We agree? So basically what I want to do is I want to prove that, for example, this value plus this value equals this value. Okay? This value plus this value equals this value. Okay, so that's what I want to do essentially for the array, but I only want to do it where there's an addition gate, and I don't want to do it where there's a multiplication gate. Okay, so we have 2 challenges that we want to solve. One is, how do we, using polynomial math, how do we check that this plus this equals this? Okay, and then the second thing is, how do we kind of limit it to just checking these addition gates, okay? I don't want to check that 6 plus 7 equals 42 because it's not true. And this is important. I also don't want to check that 8 plus 6 equals 7 because 8 plus 6 aren't even part of the same gate, okay? So this addition check, I need to start it at the start of an addition gate, okay? And only start it at the start of an addition gate. Don't start it in the middle of an addition gate. And don't use it on a multiplication gate, okay? So you'll notice that there's a 1 in my selector value at the start of every addition gate. So that's going to be helpful to me. It's going to be convenient for me to do. Okay, so what I want to do, I'm just going to pencil it in. Let's write it in array math first. So what I want to do is I want to check whether C at I plus C at I plus 1 equals C at I plus 2. Okay, so this is, if we think of it in terms of arrays. Okay. Only if S plus I equals 1. Okay, so I only want to do it at i's where S plus equals 1. So this at 0 here, it's a 1. So I want to check that 3 plus 5 equals 8. If I move over 1, it's a 0. So I don't want to check that 5 plus 8 equals 6 because that doesn't mean anything. Okay, and here I want to skip. Okay, so this condition lets me skip ahead, and I'm only ever going to check it at the start of every addition gate, and then I'm going to check that the current pointer plus the next pointer equals the next one. Does that make sense as an array? Okay. All right. Now what I want to do is I want to turn that into polynomial math because I don't have arrays. I have polynomials instead. Okay. So let me try to write it the same way. So I have P, and I have it at some value I. Okay. I'll write it as omega to the I. Let me instead, let me keep it as a variable instead. Okay, let's write it as a box here. This will be an easier way to see it. Okay, so I have P at a box. So I have the polynomial S or value. Yep.
When you wrote like S plus I, is that an equal? No.
Yes, an equal. Yeah. Sorry. Thank you. Okay. So what I'm going to check is I'm going to check the polynomial at some value I. Okay. But I'm just going to leave it abstract. How do I slide over to the next value? So I want to, in an array, I add 1 to the index, and I can slide over to the next value. Here now I have it in polynomial form. So let's go back to our picture of a polynomial. Crazy picture. Okay. How do I slide over to the next value? Okay, so I'm going to multiply by omega. Okay, so I multiply by omega, that gives me the next value over. Okay, so what I want to check is that P at box plus P at box times omega equals, now if I want to slide over 2, how do I do that? So I'm here, I want to slide over 2 elements. I'm going to multiply by omega twice, which is omega squared. Okay, so I'll write it as omega for now. Okay, but we can write that as omega squared. So I have P at this plus P at this omega. And another thing that we like to do is we call this a constraint. So that's the term. You'll hear that a lot. Like when people talk about zero knowledge, they're like, oh, I have 10,000 constraints. So constraint just says this needs to equal this. Okay? And what we do is we always try to make our constraints equal 0. Okay, so we want our constraints to be like at 0 everywhere. Then there's a way of proving that constraint is true. So what I'm going to do is I'm just going to move this to the other side. I'll make it squared. And now this is all equal to 0. Okay? So this says that this plus this minus this equals 0. Okay? Now, is that true at every point on the polynomial? It's not true. It's only true at the points where S plus is a 1. Okay, so if S plus is a 1, then that's true. And if S plus is not a 1, if it's a 0 instead, then this is not true. Okay, so this will equal 0 if S equals 1. Okay, how do I make this polynomial? Okay, let's say that S blah, blah, blah equals 1. Okay, so if S of the selector equals 1, then this constraint equals 0. Okay, that's fine. Let's say that S plus is not 1, then what's S plus going to be? It's going to be a 0. Okay, I'm trying to extract the answer from you. I think it's easier to just show you. Consider this. What if I write down this equation? Yeah. Oh, sorry. A yawn, not a question. So I take this equation and I simply multiply it by S plus. And I say that has to equal 0 everywhere. Is that true? Is that going to equal 0? And here I'm going to say 0. There's a small technicality. I'm going to say on the domain. So what I mean on domain is for all the values in the array, it's going to equal 0. For the numbers that are outside of the array, we're going to deal with that later. But this you can sort of ignore for now. But anyways, okay. So what I'm saying is that pick any value along the array. In fact, someone just shouted a number between 1 and 15. Not a hard question.
32.
Between 1 and 15.
150.
7. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, so I'm here. All right. Is this number plus this number minus this number 0? It's not. Okay, we're in the middle. We're sort of spanning two gates. Okay, but if I multiply it by S plus 0, I multiply it by 0. Correct? Is the result 0? Is this going to be 0? It will be, right? Because the S plus is 0. Yeah? So basically, at every cell that I don't care about, S plus is going to be 0. Therefore, this expression is going to be 0. And the only time I have to check whether this equation holds, the only time I need to check it is if F plus is 1. Right? If S plus is not 1, then there's no point in checking it because this is 0, so I already know that it's 0. Okay? Everywhere it's a 1, then I have to do this check. Okay? And that's the exact check that I want to do every place that it's 1, which is that this plus this equals this. Does that make sense?
So kind of this is the equation for checking addition.
Yeah, exactly. Yeah. So this is an equation that checks addition, and then by multiplying it by the selector, it makes it so that we're not checking addition at every starting point. We're only checking at the selected starting points itself. Okay. So if I can prove to you that this results in an array that's 0, 0, 0, 0, 0, 0, 0, okay, put into polynomial form, then I've proven to you that this constraint is true. And if this constraint is true, that tells you that every add gate is correct in this circuit. What does the verifier need to check whether this is correct or not? So they already have S plus. That's fine. They have a commitment to C, or to, sorry, I somehow switched to P. Well, it's the polynomial of C. Maybe I'll write PC. That actually is probably even better notation.
Sorry, can you say why when the S plus is a 1, the
Okay, so let's expand this out, and I'm going to show it to you visually as well. I'll show it to you a few different ways, and one of these ways is going to stick. Okay, so we can break it into two cases. So there's S plus equals 0 and S plus equals 1. And notice also the selector can only be binary. It's binary, so it can only be 0 or 1. Technically, you could put a 3, 4, 5, like the math isn't going to stop you, but it's set up, the verifier, when they construct it, they're going to make sure that it's binary. Okay, all right. So when S plus equals 0, this whole thing, let's give this a name. Because first off, can you multiply polynomials together? You can. You can add polynomials together. Okay. So what is this? This is a polynomial, right? Yeah. It's a polynomial. It's the sum of 3 polynomials multiplied by another polynomial. Okay. So this whole thing is a polynomial. Let's call it for fun V. So we have this V polynomial. Okay. So if S plus is 0, then V has to be 0. Okay, because V is the multiplication of this and this. Okay, if S plus is 1, is V automatically 0? Not necessarily. It's only going to be 0 when this occurs. Okay, so it will be another subcase. So we have PC plus PC. Let me just grab this. Okay. So what happens to V when S plus equals 1? Well, we have two subcases. We have the subcase where this, that's not going to fit. Okay, if S plus 1 is equal to 1, then V will equal 0 only when this condition holds. Okay, and it won't necessarily equal 0 if this condition doesn't hold. So if this condition doesn't hold, then it could equal whatever. Yeah. So I'll draw like a bottom symbol that just means like some arbitrary value. Otherwise. Does that make sense? No? Yeah. Okay, all right. So when S plus is 1, we check this condition. And when S plus is not a 1, we don't bother checking the condition. It's automatically going to be 0. Okay? So the whole thing is going to end up being 0. Okay, last thing. This is just more intuition for why this works. Okay, clear your minds, forget about PLONK circuits, everything like that. Okay, I come to you and I say, here's this polynomial. The polynomial is, it's a normal polynomial except for I multiplied everything by W. So if you want to put 5 into the polynomial and figure out what it is, you're first going to multiply 5 by omega, and then I'll evaluate the polynomial for you at that value instead. Okay, what does this mean? Like what's the meaning of this omega being inside this polynomial? How does it compare to just the normal polynomial? So consider I have a normal polynomial, okay? And now I have the same polynomial, I stuffed an omega inside, okay? So that did something to the polynomial. What did it do to the polynomial? So it does change the pointer value, but what does it do to the entire polynomial? Okay, so what it's going to do is it's going to take every value and it's going to move it over by omega. And it's going to take the next value and move it over. It's going to move everything over by omega. What happens when you move the last thing over by omega? You wrap back to the start, okay? So what it's going to do is it's effectively going to shift the polynomial, okay? So if you want to visualize what this looks like, let me grab one without so much scribbling over it. So this is P of C. Then, PC of blah. And this will be PC of blah times omega. Okay. So it's going to look exactly the same. Except for the 22 at the end, it's going to move over to here. And let me think about it for 1 second. Okay, so when you go up by omega, you're actually shifting forward. So I did the shift backwards. So 3 becomes 5. So the value at 5 gets shifted over. So I apologize, I just did the shift in the wrong direction. Okay, so the 3 is going to go on the end of the polynomial. Okay, so the 5 shifts over, the 8 shifts over, the 6 shifts over. When we reach the end, and when we start at the start, I need to shift this over, but there is no starting point, right? There's no array here. And so because of the root of unity, I stick it on the end. So I go all the way around to the end, and I stick it there. Does that make sense? Yeah. So why do we wrap? Yeah. Okay. So we have to go back to this picture. I apologize for how messy it is. What we said is when we encode the points, we're going to pick a value omega. And then I'm going to encode the next point, I'm going to multiply by omega. Then I'll multiply by omega again. It might wrap a bunch and I'll encode it. And I've chosen omega such that when I hit the last element of omega and I multiply it by omega again, it goes back to the start.
Yeah, the size is exactly the size of the
Okay, so there's got to be a relationship between, so I drew this diagram, and what I didn't say was how many times do you multiply by omega before it wraps back to 1, right? Yeah, so that's the order of omega. So the order of omega, often we call it k, so that's usually the value here, okay? And what I'm going to assume here is that, it's actually, this is a great question. I'm going to elevate it to a simplifying assumption like I made somewhere here. So I did them in green boxes. Okay, the length of this array, so the length of C, is K, and omega, the order of omega is also K. Why does this matter? What the omega k lengths of array, why does this matter? All it does is it tells you that, actually when you do this, when you multiply by omega, that the last element will wrap around, or sorry, the first element will wrap around to the last element. Okay, so this will give you the wraparound property. Now this ends up being a simplifying assumption because it's actually quite awkward. With PLONK, the length of your array is always going to be a multiple of 3 because you have a left, right, and out, left, right, out, left, right, out. In practice, most elliptic curves are not going to have a root of unity, a kth root of unity that is divisible by 3. They're going to have a bunch that are divisible by 2, and they're not going to have any that are divisible by 3, okay? So you're going to have to do something about this later. What you do is you pad the end of your array. But as soon as you pad it, it messes up these equations that we've been writing because what I wrote is true up to the padding, but then once I hit the padding, then it no longer is true anymore. And then, so then I have to do something special at the end of the padding. Adds a lot of complexity that like I don't want to get into in this class. So we're just going to assume that everything is nice and clean, and yeah, that basically this wraparound property holds. Okay. Okay. Yeah, we're out of time, so I'll pick this up next class. Thanks.